Okay, hello, Physical Science. This is Mr. B, and we're going to finish up Section 2 today. Remember, the title of this section is Speed and Velocity. We took a look at speed last time. We talked about instantaneous speed versus average speed. And now we're going to look at velocity, because like I said last video, you've probably used velocity and speed interchangeably at some point in your life, but they are different. So we're just going to dive right in to figure out what the actual difference between the two is. So velocity is a description of both speed and direction of motion. So that's the difference between speed and velocity. Speed, just how fast you're moving. When we talk about velocity, it's how fast you're moving plus the direction you're moving in, and velocity is a vector. So remember what that means. A vector is just a line, a line that has a direction and a magnitude. And again, we'll add all of our, so this is a vector, remember, and then if I added 35 kilometers above it, that's my velocity, 35 kilometers to the east, or 35 kilometers to the right, 35 kilometers in that direction. So that is what velocity is. It is a vector. So sometimes knowing only the speed of an object isn't enough. You also need to know the direction of the object's motion, which we just talked about. And then again, so together, the speed and direction in which an object is moving are called velocity. So make sure you have the definition of velocity written down. They just gave it to us 2 times in a row. So a cheetah's speed, again, just to get some examples here, might be as fast as 90 kilometers per hour. So that is just its speed by itself. So to describe the cheetah's velocity, you must also know the direction in which it is moving. So is it 90 kilometers north, 90 kilometers south, yada, yada, yada. So that is, again, the importance of velocity and how it distinguishes itself from speed. And vectors, remember, just our lines with the arrow showing the direction and the magnitude, can be used to show our changes in motion. So just like we graphed out the examples in class just with distance, now we can graph out examples with how fast things are moving. So vectors of varying length can represent motion, and each vector corresponds to the velocity at a particular instant. So the reason why we have different vectors is because the velocities are changing at different points in time. And we usually draw longer vectors represent a faster speed and shorter one a slower speed. So that's just kind of to give us another visual representation here that, again, a shorter line is going to mean that it's moving at a slower speed, where a longer line will show us it's moving at a faster speed. And vectors point in different directions to represent the direction at any moment. So again, if I have two, again, we're going to see some examples. So we can have a vector pointing to the right, vector pointing up, to show that maybe that cheetah was chasing a gazelle and it's running at 90 kilometers to the east. Then all of a sudden that gazelle changes paths, and then now it's moving north at 45 kilometers per hour because it had to change speed so quickly, or it had to change direction. So that is what the vectors are going to show us, is how fast they're moving and in what direction they are doing, and in what direction they are moving. And then another example, as a sailboat's direction changes, its velocity also changes, even if its speed stays the same. So if this sailboat is traveling at a constant 30 kilometers per hour north, then it shifts because they see a big rock face coming up, and then now they're traveling 30 kilometers to the west to avoid the rocks. Even though their speed stayed exactly the same, their velocity is different because you have to take into account our direction when you talk about velocity. So how do we actually add up a velocity? So if that sailboat, if we wanted to figure out what its total velocity is when it's moving, how are we going to do that? So we're going to add it simply by vector addition, which we have done before with our distance, or with our displacement. So it's going to be the same process that we use when we added displacements. So sometimes the motion of an object involves more than one velocity. So again, it's not always going to be the same one constant velocity. And a good example is a boat that's moving on a flowing river. So there's the velocity of the river relative to the riverbank. So how fast is the river moving while it's going along the bank, and the velocity of the boat relative to the river, and they will combine. So there's two different ones. It's how fast the river is actually moving and how fast the boat is actually moving. Then they yield the velocity of the boat relative to the riverbank. And I'm pretty sure we have a picture of that to kind of help it make more sense right here. Okay, so right here, this 5 kilometers per hour right here, this red line, this represents how fast the boat, or I'm sorry, how fast the river is moving relative to the riverbank. So our riverbank is the frame of reference. It is unmoving. So the water itself is just moving 5 kilometers per hour. So that's our first velocity. And so now the boat, it is moving at 12 kilometers per hour in the exact same direction. But now our frame of reference is the river. Because if you're this guy in the boat, to you the water doesn't look like it's moving. Or, I'm sorry, the water looks like it's moving. So the water, okay, hold on one second, I'm confusing myself here. So the water is now our frame of reference. So now it's relative to the water. So I'm sorry, so the water is our frame of reference, and we're moving 12 kilometers per hour with water as our frame of reference. So we just add those two together to determine that if we go down here, the total velocity is going to be 17 kilometers per hour. So we just take 5 times 12 when it's in the same direction. So I know I kind of butchered that a little bit. Sorry if I confused it. I'll go over an example in class to make it easier. But when we talk about the riverbank, the river is flowing at 5 kilometers per hour, so we have to take into account that velocity to the right, and then it's moving, and then the boat's moving 12 kilometers per hour on top of the 5 kilometers from the river, so it's 17 kilometers per hour. So they're in the same direction, so we simply just add them. Now, if our boat is now traveling straight at the riverbank at 12 kilometers per hour, now we have to take into account the 12 kilometers per hour that way, and we still take into account to the 5 kilometers going that way, and now we have to use the Pythagorean theorem like we had to, again, in our distances. So now our total velocity is this white line right here, so we do 5 squared plus 12 squared equals x squared, or z squared, what they have called right here, and our z is going to equal 13 kilometers per hour when we go through the Pythagorean theorem. But we're going to do definitely several velocity examples to make sure we're clear on this, because again, I don't know how well you can explain some of these math problems over a video. That's why we'll do that in class. But just be aware that velocities are added the exact same way that we did displacements. We follow all the same rules, and there's really nothing to be nervous about. So that is it for section 2. Let me know if you have any questions.